Good afternoon. My name is Ahmed Kovacevic from City University in London, and I'm in Fluid Machinery Board Group. Fluid Machinery Board Group is organizing this seminar, which is today on the future of microgas turbine technology. The seminar will be presented by Professor Abdul Nasser Saima, who is a professor of energy engineering at City University of London and the interim dean of our School of Mathematics, Computer Science and Engineering. Professor Saima was a professor of computational fluid dynamics prior to coming to City University, and it was at the University of Sussex from 2006 to 2012. Before that, he was a senior lecturer of computational mechanics at Brunel University from 2005 to 2006. And a research fellow and a senior research fellow and a principal research fellow at Imperial College from 1994 to 2005. He also held the title of Rolls-Royce Research Fellow at Imperial College from 2002 to 2005. He obtained his PhD in computational fluid dynamics from the University of Manchester in 1994. An MSc in Energy Technology for Developing Countries from the University of Salford in 1991, and a BSc in Mechanical Engineering from Birzeit University in Palestine in 1987. His current research focus is on distributed power generation using microgas turbines and organic Rankine cycles, thermal energy storage, and concentrated solar power. He has worked on large gas turbines of power generation and jet propulsion, publishing work in aerodynamics and aeroelasticity of compressors and turbines, as well as the general issues of aerodynamics of gas turbine components and external aerodynamics on aircraft. So I will now pass to a presentation from Professor Saima, after which we will have some Q&A session.
Hello everyone, my name is Abdul Nasser Saima. I am a professor of energy engineering at City University of London. I will be presenting today about the future of microgas turbine technology. There is a wide range of topics in this talk, and with the limited time I have chosen to focus on these topics. I will first give a general description of the microgas turbine systems with some perspective on the relative history or the relatively short history of these systems. I will then provide an overview of the architecture of microgas turbines and the main components and design aspects. Subsequently, I will move to some technical features that distinguish these machines from other machines providing similar power range. After that, I will go into more detail on the applications for these machines and the range of products in the market with some examples. And finally, I will conclude with some remarks. So what is a microgas turbine? It's a heat engine which has a continuous flow as opposed to the heat engines like reciprocating engines which have pulsating flow, and it provides either shaft power or can be used for propulsion or electricity generation. This requires conceptually simple component designs. These are the compressor, a turbine that are both mounted on a single shaft, and some heat addition unit. It is similar in architecture to propulsion engines that we may all know, as well as large power generation plants using gas that we call them nowadays gas power plants. For example, you can see in the middle right picture the 300 megawatt Siemens gas turbine that are used in combined cycle power plants. There is no general agreement currently on the size that can distinguish a microgas turbine from a normal gas turbine. In the past, many people designated anything below 1 megawatt as a microgas turbine. Some now designate it to anything less than 100 kilowatt. But sometimes they use that for sometimes these things in between. However, more people nowadays refer to anything to 100 kilowatt to few hundred kilowatt as small gas turbines, sometimes even in the lower megawatt range. So, how does the gas turbine work? As I said earlier, it is a continuous flow machine where air pressure is increased in the compressor. Typically, for micro gas turbine is a centrifugal compressor. Heat is then added either in a combustion chamber, in a heat exchanger, or in some application nowadays via concentrated solar power in a receiver. Hot gases are then admitted to the turbine where they are expanded to provide shaft power. The compressor is driven by part of this shaft power, and then either the electricity generator is used to or be driven by the power, or you can use this, for example, to provide a propulsion through a fan or other forms of propulsion. Turbines are typically, again, in microgas turbines are of the radial inflow type. Sometimes nowadays people may use axial turbines. Because of the relatively low pressure ratio compared to large gas turbines, hot gases leaving the turbine are at higher temperatures than the gases exiting the compressor. This provides an opportunity for what we call recuperation or regeneration, where you can use that heat to preheat the working fluid before it enters the combustor, hence reducing the thermal energy input and increasing the efficiency of the machine. And this happens because we are required here to burn, for example, less fuel for the same power output. So microgas turbine follow the Brayton thermodynamic cycle as shown on the right in its simple ideal form on a temperature entropy diagram. For those who do not know the concept of entropy, think of it as in this context as being increased by adding heat to the system. It is also associated with the heat generated in components due, for example, to friction or irreversibilities. The compression process increases the pressure and temperature, moving from the isobar 1,4 on the diagram to the higher pressure isobar 2,3. Heat is added at constant pressure between points 2 and 3, and then expansion happens in the turbine between points 3 and 4. Microgas turbines operate an open cycle where gases are ejected to ambient at point 4. In closed cycle systems, we require to have a heat exchanger to cool the working fluid and bringing the gases from the temperature at point 4 to the temperature at point 1 on the TS diagram or the temperature entropy diagram. In here, I will give some historic perspective of MGTs. The development of microgas turbine started in the late 1980s. This was driven by the automotive industry searching for an alternative to the reciprocating diesel and gasoline engines, or what we call them internal combustion engines. This drive was due to the advantages of microgas turbines regarding low emissions, fuel flexibility, and the potential to compete on cost with internal combustion engines. With the use of high-speed generators in the 1990s instead of mechanical drive, the technology became suitable for hybrid vehicles. However, at that time, the hybrid electric drivetrain was not sufficiently mature technology and did not raise further interest. Instead, the technology was picked up by the decentralized power generation market, where its long life and low maintenance cost make it compete on cost and capital for these type of applications, especially for the medium power range, say above 30 kilowatt. Progress has been slow, however, and varied from country to country, but it looks like it's picking up momentum now, particularly due to interest in reducing nitric oxides or NOx emissions. So now I will give some of the basic features of the design of microgas turbines, where we get a bit of more detail here. So at the center of the slide, you can see a cutout through a simple micro turbine showing the main mechanical arrangements and components. The design process starts typically with the thermodynamic cycle analysis and optimization, which follows a known specification given, say, by the application or the customer or for a given duty. This eventually, after a number of iterations, defines the mass flow rates of the air and fuel, the pressures and temperatures at the various points in the cycle, which are usually at the entry and exit of each component, thus allowing the start of the aerothermal design of these components. The compressor, turbine, and heat addition unit, aerodynamic design as well, are undertaken at this stage, where the flow path is defined through the compressor and turbine, allowing also for the rotational speed and blade shapes to be determined. This as well allows for example, the entry and exit to the turbine and compressor, typically on volutes, to be designed. Parallel to that process, mechanical design takes place, and it is an iterative process with the aerothermal design. And at this stage as well, a shaft bearing arrangement needs to be designed, and some rotor dynamic analysis, as you can see to the bottom right corner, need to take place to ensure that all the vibration modes are out of the operating range, to ensure vibration-free systems or low vibration during the startup and the shutdown. This also includes the high-speed generator, which typically sits on the shaft and needs to be considered during the rotordynamic analysis of the system. Not to forget as well that the bearing system needs to be defined. Many machines still use lubricated arrangements with their journal bearings or roller bearings, but some now are increasingly using air bearings, and some people are considering the use of magnetic bearings, in particular for the larger units, or what we call small gas turbines. As well as this, recuperator specifications happened during the design process, and it's again an iterative process with the thermodynamic cycle, because the specifications of the recuperator in terms of pressure loss and effectiveness affect the design of the cycle itself. As I said, the design process is iterative, so there's going forward and backward between components until a satisfactory design between all the components is achieved, and some adjustments are made during this process to some component specifications. It is also important to undertake the design of the electrical and electronic system. That includes the electrical drive, which is used for starting up the system, a rectifier and an inverter to feed the electricity generated from the system into the grid, as well as the control system. And on top of that, we need to specify places and types of sensors that need to be installed on the system, both for providing information for the control system, as well as for monitoring the operation and optimization of the operation of the device. So what are the technical features that distinguish these machines from other combustion engines? Particularly the main competitor here, as we know, is the reciprocating engines. Because microgas turbines are small, they have small parts count, so they are compact and in principle are more reliable with less downtime and less, if you like, breakdown in operation. They are more compact, as I said, and thus providing higher energy density, also facilitated by the presence of a high-speed generator, which is very small because it rotates at a very high speeds. In addition, these machines are more fuel flexible. They allow variety of fuel types and calorific values more than IC engines to be used, and they can use as well external heat sources, or they can be used with concentrated solar power. Nitric oxide emissions is a major features of these systems, is typically in the orders of, if you like, less than 10 parts per million, as opposed to about at least 10 times that for reciprocating engines. Additionally, the main source noise in these engines, which is the combustion noise, it's easily attenuated by installing upstream and downstream noise attenuating devices, but also they have no low frequency vibrations of the order that is encountered in IC engines because of the reciprocating nature of those engines. When used in combined heat and power mode, these machines can provide flexible ratio between the electricity and power demand. For example, if the heat demand is higher, you can, for example, remove the recuperator, so the electrical efficiency is lower, but you get more heat out of the system. And that is a more flexible approach than the competing reciprocating engines. They are also suitable for integration with fuel cells if high electrical efficiency is required, in particular what we call them a solid oxide fuel cell, which require high pressure and high temperature to operate them. Now, moving to the main applications of microgas turbine systems. As mentioned earlier, the main driver for recent increase in the use of combined heat and power systems is the presence of microgas turbines. Also, they are used for combined heat, power, and cooling. This applies for relatively large domestic scale as well as small industrial applications. I'm talking here for things above 30 kilowatt electrical demand. Interest in the use as automotive range extenders for electric vehicles have gained traction recently with the increased demand on electric vehicles and the increased demand that they should be driving longer distances than permissible by a single charge of the batteries. There is as well interest now in implementing them in larger transport vehicles, vehicles that used to transport goods between, say, cities where batteries cannot take these very long. There's some interest as well even for use these things to replace diesel trains with hybrid electric trains. They're increasingly used as well in oil and gas industry, particularly to burn the flared gas rather than allowing it into the atmosphere, which is currently as well in some location banned. So there is actually a mandatory, if you like, need for using machines to use this gas for other purposes. Currently, as we will see later in this presentation, they are being developed as well for distributed concentrated solar power. They are suitable for small-scale propulsion applications like small-scale UAVs or unmanned air vehicles. Not to forget the use for backup power and emergency use, although the high capital cost compared to reciprocating engines, at least until now, makes them only suitable when space is at a premium. Now we have understood the basic features of these machines and their design, we will move into their market. In here, I'm not here making a comprehensive picture of the market. It's rather more indicative and shows the main machines available. So to start with, I will say the main three market players at the moment, the largest of which is Capstan, which started with the two machines, C30, 30 means 30 kilowatt electric, and C65. And recently they have introduced the C200. As I said, this is the largest player at the moment. It's a California-based company and has many applications nowadays in Europe and in the UK. The next one is Untitled Energia. They have a single-size machine, which is the AE100. This machine actually was originally developed by Turbine, which was a spin-out from Volvo in Sweden, but this has been bought several years ago by Untitled Energia in Italy. The third available machine in the market is the 250 kilowatt MT 250 from Ingersoll Rand. To my knowledge and through my contacts with industry, I know that there are a number of products that are about to enter the market. They're really approaching very quickly. And the first of which is a very interesting machine that I will talk a little bit about it in a later slide, is the Aurelia 400. Aurelia is a company based in Finland. And then the MGT Intertwin machine, that's a very small 3 kilowatt machine for combined heat and power. MGT is based in the Netherlands. In the UK, Samad Power have produced the Turbo Green boiler, which is an electrical power of 2 kilowatt electric. And there is the NSS larger machine, 280 kilowatt. And again, through knowledge with industry, there are few in the pipelines coming at a later stage, including the Aurelia 1000, the Blade on Jets in the UK, which is a 12 kilowatt engine. And we are at City University in the process of getting close to market to micro-turbines, a 6 kilowatt engine that has been already demonstrated, as we will see, and a 10 kilowatt engine that is in the process of, if you like, completing construction and testing. So moving into the market applications, the market applications are varied, but I'll focus on few here. They're starting, for example, for the power-only applications, and the capstan engine here is an example rather than a, if you like, a general feature. Here, the C30 and C65 have 3 possible modes of generation operation modes. To the left, you can see they can be used as a base load. And in this case, they will be operating at a constant power output, which means that you can maximize the overall efficiency of the system over the period because it will operate at its maximum efficiency point. They can be used as well as load following in a similar way as large gas turbines used in the grid. Additionally, the potential use as time of use whenever they need it. So you switch them on, you operate them as needed, and then switch them off when there is no need, as there is a utility power available from other sources, as shown in the picture on the right-hand side. Some more about the capstan machines. So there is the C200 that I mentioned, which you can see it on the left-hand side of the picture, and the C1000 on the right-hand side. Some of the features of the C200, which is also similar, in fact, to the design of the C30 and C35 capstan engines, are shown in the graph. It shows that there is an annular combustion chamber and an annular recuperator surrounding the main shaft containing the compressor turbine and the high-speed generator. One of the advantages of this arrangement, it makes for a very compact system and very symmetric system. However, it has the disadvantage that it's very difficult to maintain if there's something happened in the internal parts, and it's very difficult to adapt. For example, if you want to change the combustor for a different type of fuel, you'll have to change almost the entire engine. Now, the compactness and the shape of it provides for a modular nature, and you can see the C1000 on the right actually is not a completely new machine. It's an arrangement where our 5 C200 are installed one beside each other, and they all can feed into one exhaust unit to, for example, raise steam or provide combined heat and power in a boiler. This slide basically shows how the capstan machines are used in a combined heat and power. This is just for illustration. So you can see the machine here with the shaft coming out of it, driving a generator, and then the exhaust gases going into a waste heat recovery generating unit, and then you have some flue gases passing through some filtration unit. And also you can use the downstream heat remaining as well to provide, for example, hot water, etc. So you can have multiple use for these engines. Let's now talk about the combined heat and power market for 30 kilowatt to few hundred kilowatt type engines. This is currently actually the largest market available, particularly in US and Germany and Japan. The UK market has been slow in taking these up, but it is currently emerging. In particular, customers using this now, for example, in gyms to provide electricity and heat for swimming pools and for cooling the gym, for example. And they can be used as well in care homes, in small hospitals, etc. Micro-gas turbines have high potential, though, in this case, and that's why we can see that there's probably a growth imminently coming due to their low NOx emissions, as I mentioned earlier, particularly if legislation comes along, which is expected to restrict the NOx emissions from generating engines, particularly within inner cities, which put a significant restriction on the use of reciprocating engines unless they put a post-treatment expensive equipment. Now, moving to the example of the Aurelia machine, which is a very interesting one. It's a 400 kilowatt electric engine. It has a different design philosophy from the capstan engines. It is made of components designed separately and integrated in a frame. This allows for two interesting features. The first one is the use of best available technology from the market rather than designing it yourself. For example, magnetic bearings are sourced externally, combustion chambers is sourced externally and is interchangeable. If you want to change the type of fuel used, you can just bring another combustor and easily replace the existing combustor. And because of its, if you like, loose arrangement, it's much easier to access for maintenance. However, the downside of this arrangement, the machine is large. In fact, it's larger than equivalent power reciprocating engines. One of the other interesting features of this machine, because it uses an intercooled compressor technology, its efficiency is rather high for small gas turbines. It reaches above 40% efficiency compared to around 32% for typical small gas turbines in the market. The other end of the spectrum at the lower end is the Micro-CHP for domestic application. And these are two examples rather than comprehensive picture. These are known to me well because I have contact with both companies. So on the left is the Intertwin MGT machine, and as I mentioned, MGT is a Netherlands-based company, and to the right is a Samad turbo green boiler. Both designed rather than being called as a micro-gas turbine, they try to call them as, if you like, a domestic boiler or power generating boiler, which is designed basically to alleviate the fear of customers from the name of a micro-gas turbine. The size of the market really is still very small, if it exists. There is some penetration in the market, very slow in Germany and the Netherlands, but in the UK, there are some field trials, but there isn't such for this type of machines a market as yet. But the size can grow and can benefit from feed-in tariffs, because at this size of machines you can have a feed-in tariff for feeding electricity on the grid. And these units have more potential for expansion in outside Europe as well. So this is basically my views of why so far the Micro-CHP systems have not gained traction in the market. Due to a number of challenges, and the first is capital cost combined with the lack of knowledge of the technology from potential domestic customers make it difficult to understand the value of this technology in terms of energy savings and the short payback period. This is actually compounded by the fact that there is no history of installations of these machines to show people and show how much they saved or what's the benefits to them. The other challenges that they have is the match between heat and power demand for many domestic applications is not ideal. This, however, can be alleviated by a suitable feed-in tariff to the grid or by thermal storage. But the thermal storage means that you have to have additional capital cost and use of space, which again can make it difficult to convince customers with the use of this technology. So the question is that, do we have the right business model to advance this technology in the market? Is the notion of direct replacement for existing boilers a right one, or we need a different way of financing and pushing this technology in the market? So these questions are still outstanding and require innovative ways of, if you like, introducing the technology into the market. The other thing is that, does the current energy policy framework support domestic scale CHP when it's burning fossil fuels? And how can we get effective supply, installation, and maintenance chain for a technology that's going to grow slowly at the beginning? So these are the questions that probably will be asked by any investor or company who want to take these forward. Now I'll talk about the developments that we have been working on in the last 5 years at City University of London. We have developed 2 micro-gas turbines, or I call them micro-turbines because they don't use gas. The first one is a 6-kilowatt electric engine, which has been already completed, tested in Italy, as you will show in a minute. And the second one is a 10-kilowatt electric, which has a completed design, manufacture, and is undergoing assembly and testing very shortly. So this slide shows you how we use the first engine. So we use that in a concentrated solar system using a parabolic dish that was installed in Casaccia in Italy, outside Rome, at the site of the Italian research agency INEA. And the way it operates is you have an arm at the center of the dish, which actually tracks the sun in 2 directions. And the microturbine with all its auxiliary systems sitting in a box at the focal point, and air is heated using a receiver at that focal point to replace the combustion system. So the actual system has successfully been demonstrated in the later part of 2017. So this slide shows you actually how this solar-powered microturbine works. It's pretty the same as the standard microturbine. The only thing that we're replacing here is the combustion chamber is replaced by a solar receiver, which is sitting at the focal point of the dish. So actually, some people would think that we are raising steam. We are not here. We are heating the working fluid, which is air, directly using the sun. There are, of course, certain features that had to be adjusted compared to the standard microturbine. For example, we don't have here a control over the thermal input, so it cannot be used as a control parameter in the controller. Instead, we use other innovative techniques to control the machine and optimize its operation. Finally, and before I close, I will just alert you to the existence of the newly found, I would say newly found because it's been for about a year or so, the European Micro-Gas Turbine Forum, which we have established, and we have held the first conference at City University of London last year. And the plan is to hold the next event, 26th and 27th of November in Madrid, at the site of a company called Ultran. And the purpose of this initiative is to foster the commercial deployment of microturbines by setting the scenario where all stakeholders can, if you like, share knowledge, collaborate, and discuss the roadmap to move the technology forward faster than it would happen without such a, if you like, a coordinated activity. So to conclude, this talk, I'm going to sum just up the ideas. These are mainly my own, if you like, remarks about the microgas turbine. And I believe that the market has started growing, and we are expecting that this growth would accelerate in the coming years. Existing manufacturers in the market seem to believe that bigger machines can provide more profit margins, and hence focusing their current development on these machines. We are talking about here machines in the order of hundreds of kilowatts to about a megawatt. Micro turbine market, however, especially for CHP, is still stuttering and requires a number of innovative ideas to make it materialize. We believe it has a potential, but is still yet to be seen. There is a gap in the market for machines in the range of 10 to 20 kilowatts, and we have, as you've seen, developing machines in that range, and we're trying to take these machines towards combined heat and power applications. The changing legislation regarding particularly NOx emissions may provide a significant boost to the technology moving forward. And with this, I thank you all for listening to me, and I'm happy to answer any questions.
Thank you very much, Professor Simon. And the floor is now open for questions. You can ask questions by pressing the button below the slides that were presented. And please feel free to ask any questions at this moment. In the meantime, I would like to ask first question, if Professor Simon allows me. And the question would be, you outlined very nicely challenges that this technology is facing at the moment, and you outlined that there is a forum which has been set up to address these challenges. So what are the first views or the first steps that forum will be taking to actually address these challenges and put machinery into place to be used a little bit more?
Thank you, Ahmed, for the introduction as well, and for this question. Yeah, the second forum that is being held in the week after next, will be focusing on the if you like, the business side of things, the intellectual property protection, because most of the companies that deal with this industry are small companies, and there is apprehension about sharing knowledge, sharing information. But it will deal as well with looking at business models that can suit these systems. On top of that, we are actually looking at some successful case studies, so we can learn from them and see whether, if you like, what is successful in some application can be mapped onto another application. I hope this answers your question.
Thank you very much indeed. We have a number of questions now coming in. The question is from Duk Ninh Ha, which is about how does microgas turbine compare to other technologies such as fuel cells?
Well, in terms of efficiency, of course, thermodynamic efficiency, the microturbine is much lower in efficiency, but the cost is a major factor. The microturbine technology is very well known for a while, as opposed to fuel cells, which are still, I believe, struggling with reducing the cost, and as well as reliability. As well, the materials used, I believe, are still an issue.
The next question is from Patrick Hall, which is, what's the cost per kilowatt installed, and what is the physical size?
Well, this actually depends on the as I mentioned in the presentation, some machines which are compact, like the capstan, are very small, smaller than the equivalent reciprocating engine, while the Aurelia machine, for example, is larger. So it really depends on the size of the machine, and it depends on the technology and the design. But the majority of these machines are much smaller than reciprocating engine for the same power range. I would say the cost per kilowatt in terms of installed power, again, depends on the size, but the larger machines in the order of 100 kilowatts, you're looking at about £1,000 per kilowatt. It can go up to about £2,000 per kilowatt if you go in the order of tens of kilowatts.
Thank you. Related to the first question is the question from Nigel Bond, which is on how does the solar generator compare with solar hydrogen generator? I guess this is just to that application of solar power utilization.
I'm not sure what does a solar hydrogen mean really here. Does that mean that we have an electricity and then it if you like, electrolyzes water to hydrogen? I don't know what does it mean, but just in simple terms, the solar power generator here is just you convert the solar energy to thermal power as a heat input instead of combustion. That's in the term of the technology and how it works. Now, in terms of cost, I'm not sure yet what will be the cost in the market because this technology is still under development, but the estimate in some favorable areas where there is sufficient normal irradiation, not certainly in the UK, but in areas of Southern Europe, North Africa, China, etc., we estimate that this will be competitive with photovoltaics.
Thank you very much. We hope that this answers Nigel's question. So the next question is from Tony Bates, which is on could you pair a CHP turbine with heat pumps to match electrical demand to heat output?
Again, it's not clear to me what does matching to heat pump means. Does that mean that you use the exhaust gases to upgrade the heat? It's quite unclear. If you think about a heat pump raising the temperature of, say, for example, ground heat to make it as an input to the gas turbine, I can see big difficulty in there because the turbine entry temperature of a typical micro turbine is between 800 and 1000 degrees C. So it's quite practically probably too difficult to match them.
Thank you very much.
So there's a question we have about what are the main fuels used by micro gas turbines. One of the advantages of gas turbines or micro gas turbines is fuel flexibility. So you can use gas, natural gas, you can use LPG, you can use liquid fuels, and it can go you can go to lower calorific value fuels. So it's a wide range. Of course, you cannot use any type of fuel in any micro turbine. You have to have the suitable combustor in there. But the rest of the system would be almost unchanged.
Okay, thank you very much. The next question is from Graham McLean. Do you expect there will be a market for microgas turbines as range expanders for hybrid vehicles?
This is actually probably one of the highest potential markets. The reason is you can have them small size, they're compact, and if they are running at a constant power output just to charge the battery, they can be running at a high overall efficiency. So they've got a lot of advantages. There's a lot of research and development projects ongoing now for both smaller cars, but more importantly at the larger vehicles, like for example goods transport or hybrid electric trains, small boats. So the expectation is that this market is up and coming.
If you look into this question from huge grids, are the lower nitric oxide emissions achieved across all of the potential fuels, or will the fuel flexibility be limited by future legislative values?
The typical nitric oxide emissions is related actually to the design of the combustor rather than the type of the fuel, because in a combustor of the type used in gas turbine, unlike the reciprocating engines, you don't get really hot spots. Of course, if this combustor is well designed, because there's a good air fuel mixing, you don't get hot spots, and hence you don't get the nitric oxide emission. So it's related really more to the combustor design rather than the type of fuel used.
Thank you. Related question perhaps to some of the previous question is, has application been considered where there is a intermittent power supply to individual households, like in Africa or other countries? That was from Ibiba Iroma from Vier.
I assume you mean this is a backup power supply. I'm sure this is a suitable application for those. Of course, it's dependent really on the affordability, because this would be running for small periods of time. I guess at the current state, economically, it won't really be competing with the very cheap reciprocating engines for this type of application.
Thank you. Another question from Paul Taylor, which is related to probably some questions before, is how does the kilowatt hour per square meter of solar collector compare with photovoltaics? We are looking here about using half of the surface area required for the same power output in the concentrated solar power. So the land use is almost halved. Okay. There was a question which was from Jason Macer. What are the lucrative market or investment opportunities in microgas turbine areas?
I think in the UK, we think a combined heat and power applications, particularly for inner cities, is potentially, I wouldn't say it is a lucrative, but I think it's potentially lucrative. We are actually undertaking some pilot projects at the moment to go into this area to see how it would be suitable for the market. But I think probably this is more of a question to industry.
Okay, thank you. So building energy manager Shang Chen, if I pronounce that properly, says, hi Professor Saima, do you think the continued ongoing electricity grid decarbonization will have any impact on the emerging micro-CHP industry and well-established CHP industry and applications? We are just about at the tipping point where the carbon emission of electricity generated by the CHP is about the same as the electricity from the grid.
I can see your point here. However, there are two things about that. The first one is distributed generation have a large potential for, of course, more use of heat and power. So you end up with overall efficiency of 70–80%. So definitely that would reduce the carbon emissions. But the second, of course, potential here is the use for zero carbon fuels or low carbon emission fuels, such as biofuels, or in the future fuels produced by electrolyzing water, for example, remotely. So this is the storage of energy from somewhere else, generated, for example, of large wind turbines, etc., and using it whenever needed in a combined heat and power application in inner cities, such as the use of hydrogen or the use of synthetic fuels resulting from combining carbon dioxide with hydrogen.
Thank you very much. So market-related question as well is, are any of the commercially available or near-market microgas turbines currently able to run on alternative fuels such as biogas?
Yes.
Have any been demonstrated to do so? That's from Ruth Kemsley.
Yes, they are. There is some actually, well, I'm not sure about being demonstrated in the market, but I give you an example. Capstan heavily use their machines for what we call it, well, gas resulting from if you like, the rubbish collection places. Is a biofuel, let's call it. So there's a lot of use of microturbines. So there is a demonstration of that. But there's a lot of research work as well on using other biofuels that are, if you like, synthetic biofuels that you produce from, for example, vegetable oil, etc.
Excellent. Thank you. So if we go back to some more technical questions, from Adil Kuzi Kandatil, I apologize if it's not proper pronunciation. There are two questions. One is, are we able to do multiple start-stop of the gas turbines like recipe engines? And the second question is, how long does it take for a gas turbine to ramp up to fuel power?
Well, yeah, it is very easy to ramp up, or multiple start and stop is very simple. That probably is only marginally slower in terms of ramp up or response to acceleration and deceleration than recipe engines. And that's one of the reasons actually in the early days when microturbines were tried as a replacement for cars, did not work very well, because you press the accelerator, you get a little bit of delay. But that is a marginal. So for power generation is not really a serious matter.
Thank you very much. More specific to this application, solar application, from Hassan Yildi, for the solar MGT application, what was the power output of that dish, and what are the advantages compared to Stirling engine design?
Okay, the one that we demonstrated was basically a trials one. So the power output was 6 kilowatt electric. And in fact, we started the project because the European Commission wanted to look at alternatives to Stirling engines because of their reliability issues. As you may know, Stirling engines operate by using a high pressure working fluid trapped into the engine, and sealing these is pretty difficult. So there is always leakage and deterioration of performance with time. So far as I know, these problems still outstanding in Stirling engines. So reliability issues are the main factor.
Thank you very much. We still have a few minutes. So the next question is from Jason Myers. How to match compressor to turbine unit and MGT for 6 kilowatt unit?
I'm not sure what does that question, how to match it. I mean, it's there are design rules for gas turbines similar to microturbines, and I don't think probably there's enough time to talk about the actual process there, but it's not really if that's something that you can mention in a few words, but we follow standard design rules really here.
Yes, excellent. And I would say certainly that contact details of Professor Saima could be found on City University website, and if there are more technical questions, I'm sure that he will be happy to respond to them and answer to them.
Indeed, yeah.
So another question from Patrick Hall. how long before major overhaul in hours?
We're talking here in the order of thousands, really. So it doesn't require as many overhauls as reciprocating engine, and that's one of the main advantages. You can run and run and run for a very long time before you need an overhaul.
Excellent. If anybody from the audience has any other burning, urgent question, please do send them now. There is one question here is, can we get a copy of the slides? I'm sure that Professor Simon will be happy to share them, but obviously this is I'm a Key seminar, and contacting I'm a Key, I'm sure that it will be possible to get this question.
Well, if I'm a Key is right with that, I'm happy to send them to anybody who emails me.
Excellent. Well, I think we can slowly wrap up in here. There have been quite a lot of very interesting questions, both technical, market-related, and questions for the future of the technology. Is there anything else, Professor Simon, that you would like finally to say or to convey the message?
Well, the final thing is just to reiterate that we are in 26th and 27th of November holding the European Micro-Gas Turbine Forum, and registration is on our website, www.emgtf.com. And there is further information about the speakers, the schedule, etc. So if anybody interested more, you can join us in Madrid.
Well, with this, I would like to thank you very much, Professor Simon.
Thank you, Ahmed.
For all of this, and to thank also I'm a Key for organizing this very interesting webinar. And I would like to thank you, everybody from the audience, for joining us, listening to this, and we hope that we can respond to questions if there are any more.
Thank you, Ahmed, and thanks for the I'm a Key as well.
Thank you very much, and